Welcome to Study Loop.
Okay, this problem is asking us to propose a mechanism for each of these reactions. So let's go to the first one. This one we have a secondary alcohol. We know it's a secondary alcohol because the carbon in which my alcohol is attached to is connected to two other carbons. Okay, we're transforming that secondary alcohol into this tetrasubstituted alkene. Okay, and we know it's tetrasubstituted because on each of these carbons of the alkene, on this particular carbon, for example, we have 1, 2, and then on this carbon we have 1, 2. 2 plus 2 equals 4. So tetrasubstituted alkene. Okay, so let's start off with this mechanism. So I'm going to go ahead and, because I recognize I have a super strong acid, I'm going to go ahead and protonate my most basic atom of this molecule, which is my oxygen. So let's go ahead and protonate that, resulting in water instead of an alcohol. So now I have H2O connected to a carbon. Okay, so in these types of problems, when we have first of all, an acid and then heat, the heat is indicative of an E/elimination reaction. So what we're going to do is recognize that we're going to try to make an alkene as apparent by the product, and also recognize that we're on a secondary carbon, right? Because our alcohol is attached to that secondary carbon. If we're on a secondary carbon, it's going to prefer an E1, right? Because secondary can prefer either SN1 or E1, but because it's heat, we know it's going to be E1. Okay. So because it's E1, that's going to occur in a unimolecular transition state in which I have two sequential steps instead of simultaneous steps. Okay, so that means I'm going to have to kick off my water, and that's going to be its own separate step. So that's going to result in this intermediate. So I have a positive charge on that carbon, and then my H2O right here. Okay, so right now we have a secondary carbocation. We recognize that that is decent, but it has the potential to be even better. And it has the potential to be even better because we have this methyl group right there. If we were to shift this methyl group over onto that carbon, we would result in, first of all, the relief of this secondary carbocation and the resulting tertiary carbocation right there. Okay, so let's go ahead and do that. I'm going to shift this methyl group, this one right here, onto this carbon. Okay, and that will result in the following. So I'll get my cyclohexane. I have that methyl group still there, but then I moved the methyl group over here. So now this former carbocation is now covered. It doesn't have any charge, but this carbon does. So that is a tertiary carbocation. And the driving force for that particular step is that we went from a secondary carbocation, which isn't particularly stable, into a tertiary carbocation, which is much more stable. Okay, so now we're going to go ahead and do my elimination reaction. So my elimination reaction, as I said before, this is done in heat, so that's why we prefer to do elimination reactions. My OH2/H2O, that's going to come in, and it's going to try to relieve this carbon of its positive charge by making an alkene. And in order to make an alkene, we must deprotonate a hydrogen and then kick off our leaving group, which we already kicked off our leaving group, and now we just have to deprotonate a hydrogen. So in order to make that tetrasubstituted alkene, right here, I want to make it so that I can make this carbon have one less proton. So that means I'm going to have the deprotonation of that hydrogen, moving the electrons from that carbon-hydrogen bond onto this bond, and in the process, relieving this carbon of its positive charge. So that will result in my tetrasubstituted alkene. Oops, that is not a circle. Let's see. Oops, I can't undo that, so I'll just go like this. Okay, tetrasubstituted alkene with H3O plus. Okay, next up we have, oops, that was H3O plus. Okay, next up we have this one. So again, propose the mechanism for this problem. So we have this primary alcohol, and we know it's a primary alcohol because we have the carbon that my alcohol is attached to. That carbon is connected to only one other carbon. So that's a primary alcohol. And again, because we have the presence of heat, we know it's going to be a type of elimination reaction. And because it's on a primary carbon, we know it's going to perform an E2 reaction in which we have two simultaneous steps. Okay, so let's analyze this. Okay, so the very first step is the protonation of my alcohol to form water. Oops. Okay, so protonation of alcohol to form water, which is connected to my carbon. Okay, and remember, this is going to occur in simultaneous steps. So at the same time that I kick out my water, I'm going to have the formation of an alkene. So let's go ahead and do that. I'm going to have to relieve this future carbocation by making a double bond right there. And I'm going to do that by having water come in and attacking/deprotonating this hydrogen. Okay, so I'm going to move the electrons from this carbon-hydrogen bond onto this sigma bond, and in the process kick out this water as a leaving group. Okay, so that's going to result in this product, in which I have my alkene on the outside of my cyclopentane. Okay, so this right here is obviously not that. So how do we create that? Well, it's actually quite simple because we just created H3O plus from the protonation of water. Okay, all I'm going to do is protonate my alkene like that. Okay, and I'm going to move the electrons back onto water. Okay, so if I protonate an alkene, the question might arise, where does my hydrogen go? Does it go on this carbon right here, or does it go on this carbon right there? So in order to understand this, it's best if we draw out a resonance form. So I'm going to just isolate this right now. Okay, so if I isolate that and I draw a resonance structure, I can draw basically two resonance structures of this. So I can move the electrons onto this carbon, like this, where I have a set of lone pairs there, and then I have the positive charge on that carbon. Or I can move the electrons the other direction, which would be right here. So that would mean I would have the lone pairs on this carbon and the positive charge on this carbon right there. Okay, so which one is considered to be more favorable? The one that's more favorable is the one that has the carbocation in the more substituted spot. So I can either have it on this primary position, or I can have it on this tertiary position, which is the one that we want. So that means that if I'm going to have a nucleophile at all in my alkene, it's going to be this carbon, and that's because that's the one with lone pairs. If I were to protonate this carbon, then it would result in a carbocation on this carbon. Okay, so that's why we are going to result in this. So I'm going to have the new proton, because this carbon is the one that attacked this proton over here. That's going to mean I'm going to have that positive charge right there, and then of course I'm going to have water. Okay, so that water is now going to come in and help me to make my eventual product, which is this one right here. Okay, and how does it do that? Remember, this is going to be an elimination reaction in which our final step should be the formation of an alkene. So I want to form my double bond right here. Okay, but I have this positive charge right there. So that means that I have to make this carbon, I have to relieve that carbon of its positive charge, and in the process, make this carbon have one less hydrogen. And that's exactly what we want. We want to deprotonate a hydrogen, moving the electrons from that carbon-hydrogen bond onto this sigma bond to eventually create our product, which will be this product. Okay, so that should be the mechanism. And yeah, so right here, these are all just resonance forms to help us understand the whole entire process.